When we talk about traveling to Proxima Centauri, humanity's nearest stellar neighbor at 424 light-years away, we immediately crash into the single most unforgiving barrier in physics: the energy problem. It's not a question of navigation, life support, or even time. It's the crushing mathematical reality of fuel. Every kilogram of spacecraft we want to accelerate to interstellar velocities requires exponentially more fuel to push it, which itself requires more fuel to push that fuel, creating a vicious cycle that the rocket equation describes with brutal clarity. To reach even 10% the speed of light using conventional rockets would require more fuel than exists in our entire solar system. This isn't an engineering challenge we can overcome with better materials or clever design. It's a fundamental limit imposed by the laws of physics themselves. For generations, science fiction has teased us with elegant workarounds to this problem. Star Trek gave us warp drives that bend space-time, allowing faster-than-light travel without actually moving through space. Star Wars popularized hyperdrives that slip into alternate dimensions where distance means nothing. Battlestar Galactica jumped instantaneously across the void. These plot devices serve their narrative purpose brilliantly, allowing stories to span galactic distances in human timescales. But here's the uncomfortable truth: none of these technologies exist. Not in prototype, not in theory that survives mathematical scrutiny, not even in the fevered dreams of our most optimistic physicists. Alcubierre drives require exotic matter with negative mass energy that has never been observed. Wormholes collapse faster than light can traverse them without hypothetical stabilizing materials. Quantum entanglement can't transmit matter or information faster than light. Every shortcut we've imagined runs headlong into Einstein's universal speed limit, or requires physics that simply doesn't exist in our universe. But this doesn't mean interstellar travel is impossible. It means we need to fundamentally rethink our approach to crossing the void. Instead of trying to break physics, we need to work with it. Instead of carrying our energy with us, the root of the fuel problem, we need to find energy that's already there, waiting to be harnessed. The solution isn't in some yet-to-be-discovered exotic physics or materials from science fiction. It's in a principle so simple, so ancient, that our ancestors mastered it thousands of years before they understood why it worked. The answer to reaching the stars doesn't lie in our future. It lies in our past. For most of human history, crossing vast distances meant crossing water, and crossing water meant understanding wind. The first sailors probably discovered by accident that a hide stretched between poles could catch the breeze and push their raft forward. By 3500 BCE, the ancient Egyptians were using square-rigged sails to navigate the Nile, traveling upstream against the current by harnessing the prevailing winds. The Phoenicians refined these designs, creating vessels that could cross the Mediterranean without touching an oar. By the age of exploration, sailing ships like the carrack and galleon were crossing entire oceans, carrying no fuel whatsoever, powered entirely by an invisible force that cost nothing and never ran out. These ships, the Santa Maria, the Mayflower, the HMS Beagle, changed the course of human history not through technological complexity, but through elegant simplicity. They solved the energy problem by not having one. To understand how this ancient solution applies to space travel, we need to understand what actually moves a sailing ship. Ask most people, and they'll say, the wind. But that's only part of the story. Wind itself is created by differential heating of Earth's surface. The sun warms the equator more than the poles, land more than sea, creating pressure differences that drive atmospheric circulation. The trade winds that carried Spanish galleons across the Atlantic, the westerlies that speed clipper ships around Cape Horn. the monsoons that enabled trade between Asia and Africa, all of them are ultimately powered by solar radiation. When you strip away the intermediate steps, every sailing vessel in history has been solar-powered. The sun heats the atmosphere, creating wind, which fills sails, which moves ships. It's a chain of energy conversion that starts with photons from our star. Now we face the obvious challenge. Space has no air, no wind, no medium through which traditional sails can operate. The vacuum of space is more perfect than anything we can create on Earth. A cubic meter of interstellar space contains perhaps a single hydrogen atom, compared to the 10.25 molecules in a cubic meter of sea-level air. A traditional sail hung in space would hang limp for eternity, as useless as a propeller in a vacuum. But here's where the story takes a remarkable turn. The same photons that create wind on Earth continue traveling through space, carrying momentum that can push against objects just as wind pushes against canvas. Light itself has pressure, a discovery that would have seemed like magic to ancient sailors, but is now confirmed physics, measurable and predictable. Before we explore how light can push us to the stars, let's understand why our current methods can't. Chemical rockets, the workhorses that took us to the moon and deploy our satellites, are marvels of engineering pushed to their theoretical limits. The space shuttle's main engines achieved 99.9% combustion efficiency, extracting nearly every joule of energy from their fuel. SpaceX's Raptor engine pushes methane-oxygen combustion to extremes that engineers in the 1960s thought impossible. Yet even if we achieved 100% perfect efficiency, even if we used the most energetic chemical reaction possible, hydrogen-fluorine, too dangerous to actually use, we'd still be trapped by the rocket equation. To accelerate 1 kilogram to 10% light speed would require 10 to 13 kilograms of fuel. More than Mount Everest. The problem isn't our engines. It's the fundamental physics of reaction mass. Scientists have proposed numerous alternatives, each promising to break the tyranny of the rocket equation. Nuclear thermal rockets could double or triple the efficiency of chemical propulsion by using reactor heat to accelerate hydrogen. Impressive, but still requiring enormous fuel masses for interstellar distances. Nuclear pulse propulsion, popularized by Project Orion, would ride the shockwaves of nuclear explosions, achieving perhaps 5% light speed, but requiring thousands of nuclear bombs and accepting radiation exposure that would fry any crew. Ion drives, currently operating on spacecraft like Dawn and Hayabusa 2, achieve 10 times the efficiency of chemical rockets by accelerating xenon ions to enormous speeds. But xenon is rare and heavy. Carrying enough for an interstellar journey would require strip mining Earth's entire atmospheric supply. Even antimatter, the ultimate rocket fuel with perfect mass-to-energy conversion, faces insurmountable challenges. Producing 1 gram of antimatter with current technology would cost $1 trillion and require the entire power output of civilization for a year. Let's put the challenge in perspective with real numbers. Proxima Centauri, our target, lies 40.2 trillion kilometers from Earth. Light itself, the fastest thing in the universe, takes 4.24 years to make the journey. Our fastest outward-bound spacecraft, Voyager 1, travels at 61,000 kilometers per hour, a speed that would circle Earth in 40 minutes. Yet at this velocity, reaching Proxima Centauri would take 75,000 years. By the time Voyager arrived, human civilization would have risen and fallen 3 times over. The pyramids would be 5 times older relative to the arrival date than they are to us now. The spacecraft would be an archaeological artifact from a species that might no longer exist. New Horizons, which flew past Pluto at record speed, would take 78,000 years, Even if we could maintain the Parker Solar Probe's record velocity of 700,000 km/h indefinitely, which we can't, as it's falling toward the Sun, the journey would still take 6,500 years. So, if chemical rockets condemn us to geological timescales, if nuclear propulsion can't break the barrier, if exotic technologies remain fantasy, what option remains? How do we cross the void between stars in anything approaching a human lifetime, or even a human civilization's lifetime? The answer requires us to stop thinking about carrying our energy and start thinking about collecting it. Stop thinking about fuel tanks and start thinking about sails. Stop looking for what doesn't exist and start using what's already there, streaming past us at 299,792, 458 meters per second, carrying momentum that never depletes, never runs out, never needs refilling. The solution is almost absurdly simple. We build a sail that catches light instead of wind, not metaphorically, but literally. A vast, gossamer-thin mirror that intercepts photons from the Sun and absorbs their momentum, accelerating continuously without burning a single gram of fuel. This isn't theoretical physics or speculative technology. Solar sails have already flown in space. Japan's Ikaros spacecraft deployed a 196-square-meter sail in 2010 and successfully demonstrated controlled solar sailing to Venus. The Planetary Society's Light Sail 2, launched in 2019, proved that even a small CubeSat could raise its orbit using nothing but sunlight. These are proof-of-concept missions, technology demonstrators that validate the fundamental physics. But the physics they've proven is revolutionary. We can ride light to the stars. Every photon carries momentum equal to its energy divided by the speed of light, p/EC. When a photon reflects off a mirror, it transfers twice its momentum to the surface, once when it hits, once when it bounces away. The Sun emits 3.8 x 10⁻26 watts of power, sending 1045 photons streaming outward every second. At Earth's orbital distance, this creates a pressure of 9.15 micropascals, barely a whisper, 1/10,000,000th of sea-level atmospheric pressure. A square meter of perfect mirror experiences just 9.15 micronewtons of force, enough to accelerate a paperclip at 0.01 meters per second squared. It seems laughably weak, but space offers two critical advantages: no friction to oppose motion and infinite time to accelerate. A solar sail never runs out of fuel because its fuel is light itself, streaming from the Sun for billions of years. Here's where solar sails reveal their magic. Chemical rockets burn through their fuel in minutes, achieving impressive acceleration but then coasting forever at whatever velocity they achieved. A solar sail accelerates continuously, hour after hour, day after day, year after year. The acceleration is tiny, perhaps 0.01 phalantomes, but it never stops. After one day, you've gained 86 meters per second. After a month, 2.6 kilometers per second. After a year, 31.5 kilometers per second. Already faster than any chemical rocket has propelled a spacecraft. After a decade of patient acceleration, you're traveling at 315 kilometers per second, fast enough to reach Mars in 2 months. And you've burned zero fuel, consumed zero reaction mass, depleted zero resources. The photons that pushed you are still traveling onward, ready to push the next sail that follows. But there's a catch. There's always a catch. To generate meaningful thrust for an interstellar mission, the sail must be enormous. We're not talking about the few hundred square meters of current demonstrators. We're talking about kilometers-wide mirrors, gossamer-thin membranes that would cover entire cities if spread on Earth. The engineering challenges are staggering. The material must be reflective enough to bounce photons efficiently, ideally above 99.9% reflectivity. It must be light enough that photon pressure can accelerate it, perhaps just nanometers thick, weighing grams per square meter. It must be strong enough to maintain its shape across kilometers of span without tearing. It must survive decades of cosmic radiation, micrometeorite impacts, and thermal cycling from 270 degrees C to potentially hundreds of degrees. No material on Earth meets all these requirements, but laboratories are developing candidates. Graphene membranes 1 atom thick, metamaterial mirrors that reflect specific wavelengths with near-perfect efficiency, self-healing polymers that repair microscopic damage automatically. Even if we perfect the material, building a kilometer-wide sail presents unprecedented challenges. We can't construct it on Earth. Atmospheric pressure would crumple it like tissue paper, and no rocket could launch something simultaneously so large and so delicate. It must be built in space, probably at the L4 or L5 Lagrange points, where gravitational forces balance to create stable construction zones. Robotic systems would unspool the sail material from compact rolls, using centrifugal force or electromagnetic fields to maintain tension as the structure expands. The deployment alone could take months, a slow-motion blooming of humanity's largest space structure, eventually spanning an area that would be visible from Earth as a faint star when it catches sunlight at the right angle. Once deployed, our sailship begins its journey with agonizing slowness. Starting from Earth's orbit, photon pressure provides just 0.0 Rd1 ms2 of acceleration for an optimally designed sail. The craft creeps away from Earth, gaining just 86 meters per second each day. But as it climbs out of the sun's gravity well, something interesting happens. The sail converts the sun's gravitational potential energy into kinetic energy, like a ball rolling down a hill that extends to infinity. By the time it reaches Jupiter's orbit, it's traveling at 15 kilometers per second. By Neptune's orbit, 30 kilometers per second. At the heliopause, where solar wind meets interstellar space, 45 kilometers per second. The sail has become a slingshot, using the entire solar system as its acceleration track. But sunlight alone can't push us fast enough for practical interstellar travel. As we get farther from the sun, photon pressure drops with the inverse square of distance. By Jupiter's orbit, it's 1/25th of Earth's value. By Neptune, 1/900th. Eventually, the sail provides negligible thrust, and we coast at whatever velocity we've achieved, typically 0.01% to 0.1% of light speed for realistic sail designs. At these speeds, reaching Proxima Centauri takes 4,000 to 40,000 years. Better than Voyager, but still civilization-spanning timescales. To achieve the 10–20% light speed needed for missions within a human lifetime, we need more than sunlight. We need to bring our own sun. This is where the concept transforms from clever to revolutionary. Instead of relying on the sun's diffuse light, we build massive laser arrays on Earth or in orbit, focusing terawatts of coherent light onto the sail. The physics remain the same, photons transferring momentum, but the intensity increases a millionfold. The Breakthrough Starshot project proposes exactly this, a 100-gigawatt laser array pushing gram-scale probes with meter-wide sails to 20% light speed. The laser would shine for just minutes, but the concentrated push would accelerate the probe to 60,000 kilometers per second, fast enough to reach Proxima Centauri in 20 years. Scale this up to a crewed mission with a kilometer-wide sail, and you'd need a petawatt laser, the combined power output of human civilization. But the physics works. The engineering is staggering but not impossible. Maintaining a focused laser beam across interstellar distances pushes optics to theoretical limits. Even with perfect mirrors, Diffraction spreads the beam according to the fundamental physics of wave propagation. A 10-meter transmitting mirror producing 1 micron infrared light creates a beam that spreads to 1,000 kilometers wide at 1 billion kilometers distance. By the time our sail reaches the orbit of Neptune, the laser spot is larger than Earth. Advanced solutions include phased arrays of thousands of smaller lasers that adjust their relative phases to maintain coherence, adaptive optics that compensate for atmospheric distortion in real time, and relay stations, smaller sails that reflect and refocus the beam as it propagates. The breakthrough Starshot design calls for a transmitter array 1 kilometer across, built at high altitude to minimize atmospheric interference, possibly in the Atacama Desert, where the air is thin and dry. Reaching 20% light speed is only half the challenge. Unless we want our probe to flash past Proxima Centauri in hours, taking blurry pictures as it recedes into the void, we need to slow down. But there's no laser array at the destination to provide braking thrust. Robert Forward proposed an elegant solution, a 2-stage sail. The outer ring detaches and flips around, becoming a mirror that reflects laser light from Earth back onto the inner payload section, decelerating it. But this requires maintaining laser focus across 4.24 light-years. Technically possible, but requiring a transmitter array the size of Texas. Another approach uses the destination star's light for braking. As we approach Proxima Centauri, we angle the sail to reflect its photons forward, gradually slowing our approach. This works, but requires the sail to survive another decade of deceleration, maintaining structural integrity after a 20-year journey through interstellar space. At 20% light speed, space itself becomes hostile. Interstellar hydrogen atoms, normally harmless, impact with the energy of rifle bullets. A single grain of dust carries the kinetic energy of a hand grenade. Cosmic rays, concentrated by our velocity into a deadly beam, would deliver radiation doses that would kill humans in hours. The sail itself offers some protection, acting as a shield for the payload behind it, but additional measures are essential. Designs include a sacrificial buffer of low-density material that ablates slowly over the journey, magnetic fields that deflect charged particles like a miniature magnetosphere, and a needle configuration where the payload is a long, thin cylinder pointing in the direction of travel, minimizing cross-section. For crewed missions, radiation shielding alone might mass more than the entire sail, requiring hybrid solutions where initial acceleration uses laser propulsion, but final approach uses more conventional nuclear propulsion carried as payload. A 20-year journey at 20% light speed seems almost manageable, within a human lifetime, though barely. But that's 20 years of acceleration, 20 years of cruise, 20 years of deceleration, plus exploration time. A full mission profile spans 60–80 years. No human crew could survive on stored supplies for that duration. The solution requires closed-loop life support that recycles everything: air, water, food, with near-perfect efficiency. Plants provide oxygen and food while processing carbon dioxide and waste. 3D printers manufacture replacement parts from recycled materials. Nuclear reactors provide power when far from any star. The crew might spend most of the journey in hibernation, reducing resource consumption and psychological stress. Or we might send a generation ship, where the crew that arrives at Proxima Centauri are the grandchildren of those who departed Earth. The social and ethical implications are as challenging as the engineering. If we can't achieve 20% light speed, if the laser arrays prove too expensive, the materials science too challenging, the radiation shielding too massive, we might accept longer journey times with larger, more sustainable vessels. A 1% light-speed mission takes 424 years, but might carry thousands of people in a true space colony. The sail could be augmented with nuclear propulsion for course corrections and supplementary thrust. The vessel becomes not just transportation, but a world unto itself, with forests and farms, schools and hospitals, generations living entire lives between the stars. This isn't just a mission, it's a migration, humanity's first step toward becoming an interstellar species. The sail that pushes this world ship might be 100 kilometers across, visible from Earth as a new constellation slowly drifting across the night sky.